Below is a picture of an Atwood's machine. Two masses attached to a frictionless, massless pulley. Block A is more massive than block B. Algebraically solve for the acceleration of each object. Now there are a few different ways for us to solve this problem, but one of the easier ways for me to interpret this is by treating A, B, the rope, and even the pulley as one big system, and recognizing that the system is going to have a single acceleration, even if the parts have different directions of that same acceleration. Now, A will accelerate downwards because it is more massive. B is going to accelerate upwards because it is less massive. And because they are attached by that rope, that means that they're going to accelerate together. They'll have the same acceleration magnitude, even if it's not necessarily in the same direction. Now, while I could draw an individual free body diagram for A, an individual free body diagram for B, and then try to do some algebra to set certain things equal to each other, rearrange it to solve for the acceleration, if I just use this as my system boundary, where A and B are a single system, it makes it really, really straightforward algebraically in order to solve for the acceleration. Conceptually, it can be a bit weird. Now that we have our system, though, we can shrink it down to a single dot. Now, the first force I always recommend drawing is the force of gravity, pointing down to the center of the Earth. It's usually force gravity on the system by the Earth. However, in this case, I'm just going to say it's the force of gravity on A by the Earth. Because if A is accelerating downwards, and that's the way that force gravity works, is pointing at least, we are going to be showing that that force gravity contributes to that downward acceleration. B, however, it would have a force gravity acting on B by the Earth, pointing down towards the center of the Earth. However, that's in the opposite direction that B is accelerating. B is accelerating upwards. So while the force gravity on A adds to the acceleration, the force gravity on B detracts from the acceleration. Which is why on my free body diagram, despite the direction of that force vector not making sense if we were to focus it on in terms of just the force vector of gravity for that interaction between B and the Earth. If we're thinking about our free body diagram or this force diagram as a way to explain the acceleration of our system, it makes a little bit more sense. We have more force gravity on A than we do on B. Overall, our system would be moving downwards because A is moving downwards. Now, part of our system, B, is indeed moving upwards, but if we're including that massless, frictionless pulley at the top end of our system isn't really moving. But we have part of our system accelerating downwards, which really means the system itself is accelerating downwards. We need to show those forces and explain how, well, the size of them, or the amount of them, contributes to that downward acceleration. Force gravity on A contributes to the acceleration of the system. Force gravity on B detracts from it. I now remove that coordinate system because really we don't have any other forces crossing the system boundary other than the force gravity. The tensions acting on the parts are inside that system boundary, so we don't draw them here. Nothing else is crossing it. So really, we don't need to talk about any forces on the x-axis. We don't have any other forces on the y-axis. These two forces are the only forces we really care about that contribute to the acceleration of our system. So the sum of the forces in the x direction are balanced. They're 0 newtons. We don't have any forces there. And then some of the forces vertically, they're not balanced. The two forces we have our force gravity A and force gravity B. Now I am saying that the direction of the system's acceleration is positive. So I'm saying down is positive. That's why my Fg-A, the force gravity on A by the Earth, is positive, because that's what adds to the acceleration, minus Fgb, the force gravity on B by the Earth. It reduces subtracts from the acceleration in order to algebraically solve for the acceleration of our system, which once again would be the acceleration of A as well as the acceleration of B. We take that summation equation. Sum of the force y is equal to FGAE minus FGBE. Force gravity on A by the Earth, force gravity on B by the Earth. And we just start plugging in our variables. The sum of our force, we know from Newton's second law, is the mass times the acceleration. So some of the forces on our system in the y direction would be the mass of our system, which is mass A plus mass B, times the acceleration of our system. The way we can calculate for the force gravity is mass times that gravitational field strength. So for force gravity on A, it'd be mass A times the gravitational field strength minus mass B times the gravitational field strength. Now, my mass A plus B, I can literally write just like that. Mass A plus mass B. All of that sum right there times our acceleration is equal to our gravitational field strength times mass A minus mass B. Essentially what I just did here was I factored out that G from both of these, leaving me MA minus MB. Because I'm trying to algebraically solve for this acceleration, the next step is to just divide both sides by MA plus MB, which this would be an algebraic way for us to solve for this. And this should be able to work in any situation where we are looking at an Atwood's machine.